Welcome. In this video, we're going to talk about NMR, or nuclear magnetic resonance, which depends on a combination of both physics and chemistry. And you actually are familiar with this as an MRI, or magnetic resonance imaging. And on a simple level, magnets are used to make the nuclei in atoms resonate or move. But when you call it nuclear magnetic resonance, that seems a little intimidating as opposed to just MRI, or magnetic resonance imaging. But same thing. And because the hydrogen nuclei are found in virtually all organic compounds, the hydrogen nuclei become the focus in what's called H1 NMR. So the hydrogen nuclei are going to behave differently in different compounds. And the whole procedure is going to be non-invasive since the atoms are unchanged after the test is complete, and you're just using low-frequency radio waves to create the energy, or to create the resonance. So proton or hydrogen 1 NMR signals are measured against a standard, and that standard is typically tetramethylsilane, or SiCH3 parentheses 4, which has 12 hydrogen nuclei, all in a similar environment. So the NMR signal is compared to, or relative to, the standard signal from the tetramethylsilane, and it's called the chemical shift. And the expected chemical shift for several organic groups or hydrogen environments are given in the book, page 377, or also in your reference table on table 27. So a hydrogen environment could be associated with a CH3, a methyl group, or a CH2 group, although that CH2 group could be attached to another carbon or some other group, or it could just be a CH group attached to two other things, as well as hydrogen involved in the various functional groups, like the hydrogen involved in a hydroxyl or alcohol group. So if you look at the chart, you'll see a variety of different shifts predicted for these different, what we call hydrogen environments. The other thing that it plots is what they call the absorption, and the absorption gives you an idea of how many hydrogens are present in that environment. So the amount of shift lets you know what environment or what hydrogen group is likely there, and the absorption, or the peak, tells you how many hydrogens are likely present, or how many groups are likely present. For example, if you know you have only CH3 groups present compared to just two CH3 groups present along with some CH2R groups, you would draw different structures even though they might have the same molecular formula. So let's look at some examples. First example says, draw the expected H1 NMR spectra for methane, ethane, and propane. Well, if I think about methane, CH4, it's going to have, basically it's a CH3 group with one more CH on it. So I would expect my peak to be just one peak, and the peak is going to be at approximately 0.9. 1 to 0.9 is where the CH3 peak is expected. If I had ethane, on the other hand, that would be C2H6. So now I've got two carbons, each with 3 hydrogens attached to it. I would expect the spectra to look very similar, except my peak would be larger because now I have 2 CH3 groups involved instead of just the one CH3 group involved. But I expect the shift to be at the same place. And this should have come all the way back down here. My art skills just aren't that good. But I would expect this absorption to be higher relative to this absorption. So if this one had been at this point, this one should be twice as high. And then propane is going to have a different look to it because propane has got more than one environment, so there'll be more than one peak. With propane, I've got 2 CH3 groups here, but I also have a CH2 group. And so here's one environment, and here's my second environment. So if you look, I've got a 6:2 ratio or a 3:1 ratio. So I'm going to expect a fairly high peak again at 0.9, but I'm also going to expect a peak for a CH2 group And I would expect that peak, if I'm looking at the chart here, I would expect that peak to be around 1.3 to 1.4. So I'm going to have a fairly modest peak there, and then about 3 times the peak there. And when you're comparing the height of the peak or absorptions, sometimes they talk about an integrated line to look at. That would look something like that. And again, you're looking at this space compared to this space when you're looking at that. So what if you had an isomer of pentane and you want to know which one would have the least number of peaks on an H1 NMR? And then also give the absorption or peak area ratio for each isomer. So first of all, you have to realize pentane has 3 isomers. I could have straight chain pentane, and so it's got CH3 groups on the end, and it's got identical or virtually identical CH2 groups in the center. So again, this spectra, I would expect, I've got 1, 2, 3, 4, 5, 6 of the CH2 groups and 6 of the CH3 groups. So I'd expect these peaks to look rather identical at 1.3 and 0.9. But if I have methylbutane, 2-methylbutane, where I've got a CH3 group here, as well as at each end, and a CH2 group. So up here I should say my absorption peak ratio is just 1 to 1 here. I've got 2 peaks and I expect them to be the same height. But now I've got CH3 groups, and I've got them in 2 slightly different environments because these CH3 groups, are close to the methyl here, the carbon, whereas this one is further away. So this is going to be a slightly different environment and going to have a slightly different peak. So I've got one environment here, a slightly different environment here, and a third environment here. And I notice I've got a 4th one because I forgot to put my hydrogen there, and a 4th environment here. So I'm going to see a 6 to 3 to 2 to 1 peaks going on with this particular isomer. And then my last isomer is like this, and now I've got just one single peak, and this is what the question was asking, is which one of these only gives a single peak? And it would be the 2-methyl propane giving the single peak, and so the ratio is simply 1 if there's only one peak. On the second try, it says draw the structures of the 3 isomers for C3H8O. So I'll start with that before looking at the other questions. So if I have 3 carbons, I could have an OH group on the end and then 7 other hydrogen to make C3H8O for 1 propanol. I could also move that hydroxyl group to the center carbon to make it 2 propanol, and it would still be C3H8O. And then the third isomer is going to have to be an ether instead of an alcohol, so that I still have 8 hydrogens on here. So then looking at the spectra and the various peaks there, first it asks what causes the peak at 0? Well, the peak at 0 is always caused by your standard. So the standard is going to give a peak at 0 to let you know you're calibrated and all that good stuff. And then it's these other 4 peaks that I'm interested in. And my third and fourth question says, identify the groups responsible for each peak seen and identify the correct isomer making up this compound. Well, it's actually easier to answer the last question first because I know I have 4 peaks, which means I need 4 different hydrogen environments. So if I start with my last isomer, I have one hydrogen environment with these CH3s, and I have a second hydrogen environment here. Now it's possible this CH group is slightly different than this CH, so I possibly have a third environment here. When I look at the 2-propanol, I have an environment here, and these are definitely the same environment. I have a second environment here, and I have a third environment here. So far I only have 3 environments, but I see 4 peaks here. So when I look at my final isomer, I have an environment here, I have an environment here. Now it appears that my 2 CH2 groups have the same environment, but this one's attached to 2 carbons, and this one's attached to a carbon and a hydroxyl group. So that is going to give me different peaks. And if I want to know which peak is associated with which item, this would be my CH3 groups, because that's going to be around 1. One of my CH2 groups should be around here, and my other CH2 group around here. And then my OH group is the one that has some range to it from 1 to 6, so this is likely the OH group.